Recording has started now, so good evening. Welcome to this session on the ideal gas law. This is what we're going to be having a look at today. The key to understanding the ideal gas law is to really understand the nature of gases themselves and what a gas is. And sometimes some of these things are a little bit overlooked. We need to be really clear on what we mean by gas pressure, for example, because that's one of the key components of the ideal gas law. And we're actually going to have a look at how the ideal gas law was developed from the individual gas laws that contribute to make it up. So we're going to look at the individual gas laws and derive them and then combine them to produce the ideal gas equation. Make sure we're clear on what we mean by an ideal gas, and make sure that we can convert the units in the ideal gas law from one form to another to ensure that they're correct, and there'll be one past paper question at the very end. Okay, so gas pressure is one of those things that's sometimes overlooked, but like I say, it's key to understanding the ideal gas law. And gas pressure is just a measure of how frequently the gas particles contained within a particular volume collide with the inside surface of their container. So that's what it is. Pressure is, you can think of pressure as collisions with the outside per second. So there are things that you can do to increase how often the gases, part of the gas particles, collide with that inside surface. So with this in mind, quick question for you. So I'm sending to you now. So which of these following factors could increase gas pressure? Would increasing the temperature increase gas pressure? Or that reducing the volume of the container, increasing the number of moles of gas? Or could all of them cause an increase in the gas pressure? So that poll should have come through, A, B, C, or D. And the answers have come through. And yes, the answer is D. They all will. Temperature, you can think of in terms of gas behaviour, you can think of it as the speed at which the particles are moving. So if you increase the temperature, you increase the speed of the particle, which means they will reach the outside of the container more frequently, and that increases the pressure. If you reduce the volume but keep the temperature the same, then the particles don't have as far to travel, so they'll hit the side of the container more often, even at the same speed. If you put more moles of gas in there, even keeping all the things the same, then the more particles will collide the outside more. That's the equivalent of inflating a bicycle tire, for example. So yes, all of those will cause an increase in pressure. Okay, so we're going to have a look at some specifics then, and this is our way into understanding the individual gas laws. So here is another question for you. If we keep temperature constant, what effect would reducing the volume of the container have on the pressure? Would it increase it? Would it decrease it? No effect. Okay, so we're keeping temperature constant, so the particles are moving at the same speed. So if we decrease the volume of the container, it means the particles don't have as far to travel to reach the outside of the vessel. So the result would be an increase in gas pressure. I'm just waiting for the slide to update. Seems to have gone slow for a moment. Okay, there we go. You would have an increase. This idea, this relationship between gas pressure and gas volume is known as Boyles' law. And Boyles' law just states that if temperature is constant, then pressure is inversely proportional to volume. So if you increase the volume, you reduce the pressure. If you increase the pressure, you must reduce the volume of the container. Robert Boyle was a British scientist who carried out a great deal of work on the nature of gases. He worked with Isaac Newton, amongst others. The diagram at the bottom gives you the idea. If you have a look at those two containers, assuming that they contain the same number of moles, assuming that the temperature is the same in each case, reducing the volume will cause the particles to hit the outside more often. So reducing volume produces a proportionate increase in pressure. So pressure is proportional to 1 over the volume, or the inverse of the volume. You can rearrange that equation to say the pressure multiplied by the volume is proportional to 1. We can actually get rid of the proportionality symbol by introducing a constant to this equation. So the pressure multiplied by the volume will always give you the same value for a particular gas, as long as you keep temperature the same at all times, as long as you keep the number of moles of gas the same at all times. But because the product of the pressure and the volume, the value that multiplying those two things together produces is the same, then that also means, I have a little delay here. I'm not quite sure exactly what it is, but hopefully it will resolve very soon. I'm trying to update my to the next slide. My light's going quite so slow at the minute. But basically, whilst we're waiting for it to load, I will tell you, the pressure multiplied by the volume before you make a change will be equal to the pressure multiplied by the volume after changing one or both of those things. So if you double the pressure, you will halve the volume. The pressure multiplied by the volume doesn't change. There we go. So the pressure and the volume is the same before and after a change. So the terminology that is used to illustrate this is the idea that you have P1 and V1. P1 and V1 are the initial pressure and volume. P2 and V2 are the final pressure and volume after you make a change. So if you keep the temperature the same and you double the volume, you must halve the pressure. If you increase the volume by a factor of 10, you must reduce the pressure by a factor of 10, and so on. Pressure times volume equals the same numerical value every time, as long as you keep temperature and number of moles of gas the same. So that was Boyle's law. That was the first gas law that came about, hot on the heels of Boyle's law. Well, next we consider the relationship between volume and temperature. So there's another question for you. This time we're keeping the gas pressure constant. What effect would reducing the volume of the container have on the temperature? So pressure is being kept constant. We are maintaining the same pressure. So I'm just sending the survey now for the poll. Pressure is kept constant. If you reduce the volume, what effect will that have on the temperature? Okay. He asked this question. Well, we're keeping the pressure the same. That means that the rate at which gas particles are colliding with the outside of the container is kept the same. If you reduce the volume of the container, you reduce the distance that the particles have to travel to collide with the outside. That means that to maintain that rate of collision, the temperature would have to decrease. They would have to travel slower to hit the outside, whilst maintaining the pressure. So we'll look at this in a little bit more detail now, just to try to illustrate this idea, because this is perhaps conceptually a little bit more challenging to visualize. This law is Charles's law. We probably should say Charles's law because he was a French chemist and he investigated the relationship between volume and temperature. So he said that if you keep pressure volume constant, then volume is directly proportional to temperature. So if you were to increase the volume that the gas is in order for it to maintain pressure, in order for the collisions with the outside of the container to be constant, the particles would have to travel faster in order to be able to hit the outside of the container at the same rate, to have the same number of collisions per second with the outside. And the opposite applies, the example that we just did. If you reduce the size of the container, the gas would have to slow down. Otherwise, it would collide with the outside more often and the pressure would increase. You're keeping pressure constant, so that can't happen. So if you reduce the size of the container, the gas has to travel more slowly in order to collide with the outside of the container at the same rate, number of collisions per second. So looking at this from a mathematical point of view, what we are essentially saying is that at fixed pressure, the volume of the gas is proportional to the temperature. If you increase the volume, you have to increase the temperature by the same proportion to maintain the number of collisions with the outside container per second. So if you rearrange that equation, it becomes the volume divided by temperature is proportional to 1. We can remove, again, our proportionality sign by saying that the volume divided by the temperature is equal to a constant. And as long as pressure is kept the same, as long as the number of moles is kept the same, that constant won't change. Just like the previous example, we can then say that if the volume divided by temperature, the value of that sum stays the same, then we can introduce this idea of the volume in the initial stage and the volume in the end stage. So volume 1, temperature 1, the initial volume, the initial temperature, and volume 2, temperature 2 are the final volume and final temperature after a change has been made. So double the volume, you must double the temperature. Multiply the volume by 10, you have to multiply the temperature by 10. Half the volume, you would then half the temperature in order to maintain that mathematical relationship. So we've looked at pressure and volume, we've looked at volume and temperature. There's only one more variation that we can consider, and that is pressure and temperature, the relationship between pressure and temperature. So this time the volume of the container is being kept the same, and we're interested in the effect of increasing the pressure and the effect that that has on the temperature. So again, a poll question for you, which I will send to you now. If volume is kept constant, so we are not changing the size of the container, if we increase the pressure, what effect will that have on the temperature? And again, think of it in terms of the behavior of the gas particles. If you're keeping the volume the same, you're increasing the gas pressure, the number of collisions that the gas particles have with the outside of the inside of the container per second. What must therefore happen to the temperature? So I'll give you a moment to put with your answer for that. Okay, so the answers are in. We keep the container the same size. If we the only way we can cause the particles to collide more often with that inside surface of the container is by increasing the temperature. So the answer is A, there must be an increase in temperature. So this was Boyles. He is another French chemist who investigated this. I was just reading a little bit on the history of Boyles because I don't know a great deal about his achievements. This was by no means the only achievement. He was the co-discoverer of boron. I believe he also, in collaboration with other scientists, is responsible for the formula H2O. He and his colleagues were the first people to identify that water was made of 2 parts hydrogen to 1 part oxygen, something we take for granted. There was a time when people simply didn't know that, and he was part of the team that came up with it. So his place in the history of chemistry is assured. But he also gave us his own law, which, like all good scientists, he named after himself. And he recognised that if you keep the volume of a gas constant, then pressure is directly proportional to temperature. So the diagram there hopefully gives you an idea of what we're saying. If the only way that the particles can collide with the inside the surface more frequently, i.e. pressure increases, is if they are travelling faster, i.e. the temperature increases. Those two things are proportional to each other. So pressure proportional to temperature, pressure divided by temperature is proportional to 1. Again, we can remove our proportionality sign quite easily by introducing a constant. So we can say that the pressure divided by the temperature equals a constant. As long as we keep volume the same, as long as we keep numbers of moles the same, that constant will also remain the same, which means that we can do what we did before. We can consider pressure and temperature before a change and after a change. And it's actually shown on the diagram at the bottom. Same idea as before. Initial pressure divided by initial temperature will equal final pressure divided by final temperature. What the delay here is, but there we go. That's the point that I was getting at before. So again, you can consider initial situation and a final situation. So we have 3 gas laws. We have Boyles, Charles, Gay-Lussac's, and of course we can combine all 3 because we might not want to just change one thing. We might not want to keep the volume constant or the temperature constant. We might want to change 2 of them. We might even want to change all 3 and see what the effects will be. We might want to increase the pressure a bit, reduce the temperature a bit, and see what volume of container will be required to do that. So they combine quite easily. They combine in this way. Initial pressure multiplied by initial volume divided by initial temperature equals the final pressure multiplied by final volume divided by final temperature. Of course, this assumes that the number of moles is being kept constant. This used to be taught in GCSE physics. I don't know if it still is. I hope so. I quite enjoyed doing this sort of stuff. And it's not routinely required for A-level chemistry, but I think it's a good illustration of where the ideal gas law comes from, where the ideal gas equation comes from. Just like before, we know that P multiplied by V divided by T will always give you the same numerical answer. So we can make that equal to a constant. And that's what we do. And it has a name. You've come across it before, I'm sure. It's called the ideal gas constant. We don't call it constant or K. We give it the symbol R. So if P multiplied by V over T equals R, we can rearrange to put the T on either side, and we can say pressure multiplied by volume equals R, the gas constant, multiplied by temperature. We can then ask ourselves this question. Well, if we increase the number of moles, in fact, if we doubled it, if we doubled the number of moles, but we kept the volume of the container the same, we kept the temperature of the container the same, so they have to travel the same distance to reach the outside the container, they're traveling at the same speed, what would happen to the pressure? So we put twice as many particles in there, same container, same speed. What would happen to the pressure? It would double, because you've got the same number of, you've got the same container, same speed, twice as many particles will collide with the inside surface twice as often. That's the definition of pressure. So the pressure will double. What that means is that we can put the number of moles onto the right-hand side of this equation, because we know that doubling those number of moles will double the pressure, trebling them will treble the pressure. We can factor the number of moles into this equation, and that is what we do. We come up with this final equation: PV equals N for number of moles multiplied by the gas constant multiplied by the temperature. Perhaps the most critical parts, well, there are many critical parts using this equation, but I think one of the most critical parts, certainly one of the things that A-level students often make a mess of, is the units. The pressure must be given in pascals, the volume in meters cubed. I think that one is particularly tricky because students are used to working in centimeters cubed or decimeters cubed. We've got to go to meters cubed. The gas constant, usually given in the exam, but I'd hope that you remember it. It's 8.31 joules per mole per Kelvin, and the temperature is in the Kelvin scale, which is not quite the same as the Celsius scale. So let's just take a little bit of time before we look at those units, just to consider what we mean by an ideal gas. Sometimes this is a 1 or 2 mark question in the exam, so you need to be aware of it. What do we mean by an ideal gas? What assumptions are we making? Well, first of all, we assume that the gases are made up of molecules or possibly atoms, which are in constant random motion, straight lines, and they behave as a rigid sphere. Obviously, the shape of the molecule will depend upon the nature of the molecule itself, but we assume that they are rigid spheres. We assume that pressure is due to a combination of collisions between the molecules and the walls of the container. We assume that there is no loss of kinetic energy during the collision. That probably doesn't happen, but we accept it as an assumption. We assume that there is proportionality between the temperature and the average kinetic energy of the molecules. This is an interesting one. We assume that the intermolecular forces are negligible. That would make sense, because if there were intermolecular forces acting between the molecules, then you would expect it to be liquid. But of course, if you are at a phase very close to the gas-liquid phase, then there will be some intermolecular interactions, but we just assume that they're not happening at all. And we also assume that the volume occupied by the molecules, the gas particles themselves, is negligible relative to the volume of the container, which is a reasonable assumption to make when you consider that in the gas, the particles are very, very far apart. So the volume of the molecules themselves and the gas particles probably will be very, very tiny compared to the whole container. So it's a relatively safe assumption to make. So those are the ideal gas assumptions. Just to be aware of them. You might be asked to state one of them for 1 mark in the exam. You can take your pick really, and you can see other sources which will have other comments on the assumptions that are made, but I think these ones are fairly comprehensive. Okay, so let's consider these units then. Converting the units is a thing that often trips people up. So you must give your pressure in pascals. We're beginning with pascals here. So 100,000 pascals. I've chosen that figure because it's very close to atmospheric pressure. There are 1,000 pascals in a kilopascal. So if you want to convert pascals to kilopascals, you would divide by 1,000. If you want to convert kilopascals to pascals, you multiply by 1,000. So 100,000 pascals would be 100 kilopascals, which would be 0.1 megapascals. You would multiply megapascals by 1 million to convert to pascals. If you're given pressure in kilopascals, you'd multiply by 1,000 to generate the pressure in pascals, but that is what it must be. It must be pascals. The volume, this is the one that often people get wrong. The reason people get it wrong is because they think, well, there are 10 centimeters in a decimeter, and there are 100 centimeters in a meter. So that is where this problem often arises. What they fail to recognize is that we're not dealing with centimeters, we're not dealing with length, we're not even dealing with area, we're dealing with volume. So you have to cube those values. So whereas there are 10 centimeters in a decimeter, there are 10 times 10 times 10 centimeters cubed in a decimeter cubed. 10 times 10 times 10 is, of course, 1,000. So there are 1,000 centimeters in a decimeter cubed. The same logic applies going from decimeters cubed to meters cubed. There are 1,000 decimeters cubed in 1 meter cubed. So if you are given the volume in decimeters cubed, you must divide it by 1,000 to convert it to meters cubed. If you're given the volume in centimeters cubed, you must divide it by 1,000,000 to convert it to meters cubed. Kelvin, relatively straightforward. All you do is, if you are given a temperature in degrees Celsius, and you probably will be, you have to add 273. The Kelvin scale is essentially just resetting the Celsius scale. The actual divisional sizes are identical, so a temperature increase of 10 Celsius is identical to a temperature increase of 10 Kelvin. The difference is the starting point. The Celsius scale begins at the freezing point of water. When Anders Celsius developed the scale, he based it entirely on water. He took the temperature at which water froze, he took the temperature at which water completely turned into gas, and he divided it into 100 equal units and used that as the basis of a scale. And we've been using it in Europe very much so ever since. All that Kelvin does is changes the starting point of that scale. It sets the starting point at absolute zero. An absolute zero is approximately 273.15 Celsius, but we just go for minus 273. So minus 273 Celsius is 0 Kelvin. You want to convert Celsius to Kelvin, add 273. That's it. Okay, so a little bit more audience participation now then. Let's try some of these. Let's make sure we are confident converting these scales. First one is on its way to you now. I've given you a volume in centimeters cubed. Can you convert that volume in centimeters cubed to meters cubed? Okay, so centimeters cubed to meters cubed, you divide by 1,000,000. 37,500 divided by 1,000,000 is 0.0375. Okay, so this time megapascals to pascals. Can you make that conversion? Paul is on its way now. Okay, so megapascals to pascals, you have to multiply by 1,000,000, so that would make it 101,000 pascals, which is very close to typical atmospheric pressure. And finally, what is 1,000 Kelvin in Celsius? Okay, so if we're converting 1,000 Kelvin into Celsius, we're not converting Celsius into Kelvin, so we're not adding 273, we are subtracting 273, so that would make it 727 Celsius. Okay, so we're going to round up then with a recent example from the exam going back a couple of years. This is quite a tricky ideal gas law type calculation. You were provided with a scenario where there are two flasks separated by a separating tap. and you are given the volume of flask Q. You are told it has a volume of 1 times 10 to the power 3 centimetres cubed. But very kindly giving you in centimetres cubed rather than metres cubed, which of course they will do. You are told that it's filled with ammonia. The gas is irrelevant at this stage. You are given the pressure of 102 kilopascals, again, not in pascals. You're given the temperature of 300 Kelvin. They've given you that much. So hopefully you're not going to start converting it into Celsius, because that would not be the right thing to do. And the task is calculate the mass of ammonia in flask Q. Give you an answer to the appropriate number of significant figures. Okay, well, before we do that, let's make sure that we can convert the units correctly. So those are your 3 possibilities right there. The poll has been sent to you. What would be the correct conversion for those 3 particular units? Okay, so let's check this one then. We've been given the volume in centimetres cubed. 1 times 10 to the power 3 will be 1,000. We have to divide that by a million. So 1,000 divided by a million would be 0.001. So that narrows us down to B or C. Pressure is in kilopascals. That has to be multiplied by 1,000. So that will give us a value of 102,000 pascals. So the correct answer, the correct conversion is C. So let's have a look at the sum then. So if you manage to get that far, there is a mark for rearranging n equals PV over RT. That was allowed in the working. You're not required to state that explicitly unless you're told to. It's good practice to do that. It's good practice to write it out, and then you can make sure you're going about things the right way. So the pressure multiplied by the volume, if you've done your conversions correctly, as per the previous question, you end up with 102,000 multiplied by 1 times 10 to the power minus 3. Divided by the gas constant 8.31, multiplied by the temperature 300. That gives you the number of moles of ammonia, 4.09 times 10 to the minus 2. So you get that mark for the number of moles or for clear working. And then you would have to convert that number of moles to mass in grams by using mass times formula mass. The formula mass of ammonia is, of course, 17. So that will give you a final answer of 0.696. All the values that you've been given in the question are to 3 significant figures, so that is a clear indicator that they are looking for an answer to 3 significant figures. You can report it to that level of precision with confidence, and that's what you should do. A little bit of deviation was allowed for rounding errors. 0.695 to 0.697 was acceptable here. Okay. So that is the first part of the question. Not too bad, I don't think, as long as you get your units conversions correct, you can work your way through that question. The next one, well, it's pretty obvious and says if they've connected 2 flasks with a tap and one of them has gas in it and the other is empty, then obviously that tap is going to be open to allow the gases to mix between the 2 flasks. That's going to be the gist of the question here, the next part. And sure enough, here it is. The tap is opened. Ammonia passes from into flask P. The temperature decreases by 5 Celsius. The final pressure in both flasks is 7.75.0 kilopascals. Calculate the volume in centimetres cubed of flask P. So what you're going to have to do here is essentially recalculate PV equals nRT. you use the number of moles from the previous question. So you have that. You have a new temperature. It's decreased by 5, so clearly that's going to be 295 Kelvin. And the pressure is 75 kilopascals. So you have the job of converting your units. I'm sure you can do that by now. So the pressure at 75 kilopascals would be 75,000 pascals. So what we are going to do is work out the total volume. All you can do using the ideal gas law is work out the volume of P and Q combined when the gas is occupying both vessels when the tap is open. So you can do that, and you would end up with a value of 1.34 times 10 to the power minus 3. That, of course, will be meters cubed. So the volume of Q in meters cubed was given in the question as 1 times 10 to the minus 3. So the volume of P will be the difference. It will be the difference between the total volume, which is calculated using the ideal gas law, subtract the volume of bulk P, which will give you a final answer of 3.442 times 10 to the minus 4 meters cubed. Now be careful, because in the question it says calculate the volume in centimeters cubed. So for the final mark, you must convert that volume to centimeters cubed by multiplying by a million. So 3.42 times 10 to the power minus 4 multiplied by a million brings you a final answer of 342. You can see that they allowed a bit of a range here on the final answer, allowing for rounding errors and what have you. So yes, it tells you in the mark scheme notes that they allowed a little bit of a range there, but anything between 310 to 342 was accepted. It indicated the correct approach and the correct reasoning. Okay, so we are almost done. I just want to conclude by looking at what the examiners said about this question here. They said, because this was in 2015, so it was the first year they came out, the AS exams came out. Perhaps, no, was it 2015, 2016? I can't even remember now, but it was one of the first tranche of exams. It might be 2016. Anyway, it was similar to questions asked in the previous spec. 5.1, well answered. Common mistake was to use values with incorrect units for the variables. I remember from marking this, so many people got the unit conversions wrong, and well, you know, it seemed very surprising, but there it was. Question 5.2, not answered as well. A lot of people, a lot of students, spelling mistake, not mine, calculated the total volume of the two flats, but didn't subtract one from the other, didn't give it in centimeters cubed, didn't answer the question. So just be very much aware of that. Okay, so that concludes this session this evening on the ideal gas law. I hope you found it useful. If you have any questions, please enter them on the text box. I'll stay online for a little while, but if not, I will just conclude the recording there.